Okay, now I'm going to speak about another story. Which is again will in the end will be a story about some coupling and conformal theories. But first I need to say something about what I'm going to couple. I'm going to speak about vertex algebras which depend on three parameters, and at least sometimes they are denoted by in this manner: L, Y within this L, M, and N, where this L, M, and N are non-negative integers. They appeared, I would say, quite recently, like more or less 3 years ago, I think. So, I mean, probably the person who wrote more than any other about this is Miroslav Rabchak. His first paper where they appears with Gayota. Also, they appeared for another reason, I would say, with another description with a paper by Losha Litvinov with Spodeneika. And somehow implicitly, so less explicit, that in this paper they appeared in our paper with Borefegen and Grishemerson. So there is some list of names, but to be honest, it's easier to list names than give a clear definition in this case. There are different ways to think about this algebra. First of them, which was implemented in the first work by Gayot and Rabchak, they obtained it by certain combination of Kasias and Drinfeld-Sokolov reductions, somehow conjecturally. And I'm not going to say about it. I will speak about what I know better, so about these Russian papers. And in that, this algebra is constructed using screenings. Also, this algebra is constructed as a quotient. So first, let me recall that there exists an algebra W1 plus infinity. What is it? I would probably say there are two similar but different things which appeared in the literature and has this name. One of them is just Lie algebra of the differential operator. So, and another of them will be generalization of that Lie algebra. So first, there exists. Okay, let me write as an example. Oh, okay. No. What I'm going to say is that this algebra W1 plus infinity, this is a vertex algebra. Generated in PPW sense by fields W1, W2, W3, and so on, up to infinity, such that each Wn has conformal dimension of spin n. And this algebra depends on two parameters. A bit, well, one can think about them as some sort of two central charges. Besides, only one of them is probably central charge of this algebra actually, and another just the parameter in the structure constant. And it will be convenient for me to write these two parameters as epsilon 1, epsilon 2, and epsilon 3, under the condition that sum of them is 0. Let me say in words. First, W1 is just the field of the conformal dimension 1, so you can think that this is just d5, derivative of the some bosonic field. W2 can be viewed as a Virasoro. And W3 is a third additional generator, which in fact, together with Virasoro and W1, generates the full algebra. So any other current can be obtained in the OPE of this. So here I mean PBW generation. So here I mean that the vacuum model of this algebra W1 plus infinity has a basis of the following. So we have some vacuum and then apply some components of W1, then components of W2, these brackets maybe I can write without brackets. I introduced some notation for the components. I write WD of Z is a sum of double over integer n, n, WDN, Z in power minus n minus d. And then I apply this. First I apply the components of the first vector, minus n1, minus nk1. Then I apply components of the second vector, m1, and so on. And this n are supposed to be ordered. For example, n1. And they are ordered, and n1 is start from 0, m1 start from 2, next starts from 3, and so on. So on the on the vacuum model, on the highest value vector, the first component of W2, so say L minus 1 x by 0, then for W3 generate the first two components x by 0, and so on. Yes, this is a vertex algebra. This is conformal limit of what you like. What is K1 is the index, some number. I mean,
is that right?
I have a couple of, I have some sort of sequence of Young diagrams. One of them is N, another is M, and then I don't have notation. But this is a PBW theorem, nothing more. PBW statement. Okay, so you see, I don't give a definition. I state some properties, and I probably can add more property. For example, one more property is that there is a quotient of there's a map of this W1 plus infinity to W algebras of GLN. If you want W1 plus n. Yes, W1 plus n, I think. This notation which maps so I recall that the W algebras for GLN, they are generated by just n fields, W1, W2, and so on, Wn. So one can think about this W1 of infinity is the limit of this W algebras when n goes to infinity. That's so all structure constants of this W algebras analytically depend on n and also on central charge of this W algebras. So these two parameters of this W1 plus infinity are C and n. And if this second parameter, which is n here, become integers, then this algebra has a quotient, has an ideal, and factor with respect to this ideal is the ordinary W algebra of GLN. I think I was a bit wrong. So I think if we speak about this algebra, then we have epsilons and also have one more parameter, which I don't know how to denote. U say, and and everything actually depends on their ratios. So these epsilons are somehow only it is one parameter, and another is u, and if this u becomes integer, then we have ordinary W algebra. But maybe later we will see and correct this. I didn't give a definition of this W algebra. At least some properties. You can ask whether this algebra with such properties exists, whether it's unique, and and I think this is proven now. Correct with spelling? I think. Lynch. He wrote a paper, I think, 17 probably, where with a proof existence and uniqueness of such algebra. This W1 plus infinity vertex algebra.
You mean uniqueness with properties which you...
Yes.
Not the list of your properties.
No, I think the list of my properties. That this algebra generated by these fields is dependent on two parameters. I think this. Maybe there should be some conditions like simple, but I don't know. Maybe I forgot lost some property. It's quite natural. As an example which you can have in mind is a W1 plus infinity Lie algebra. This Lie algebra generated by elements of the form here n is integer and m is of course non-negative integer. And commutation relations of elements of such form is just commutation relation of differential operators, and this is a central extension which I don't write here. So you can think that we have just our generators 1, x squared, and so on. Then you have, let me denote this x d over dx by d. We have d x d x squared d and so on. So this first column is a field W1. The second column is W2 and so on. This is a list of, this is an example. In this Okay. Concerning representations as double algebras, it is somehow sometimes better to consider not it, but very related object, which is affine Yangian.
Before we proceed to affine Yangian, what does the word example mean?
It means that for special values of epsilon, this vertex algebra is a vacuum model of this Lie algebra. So usually this vertex algebra is not vertex algebra for Lie algebra, but okay. To the algebra, to the Yangian. I don't know how to say it as a theorem, but on the practical level, if you take representations like of this Yangian, you have action of this W1 plus infinity on them. This Yangian is generated by okay. Okay, I think it will be easier for me to say it now that all of this could be viewed as a conformal limit of so this double Yangian is a conformal limit of the toroidal algebra. This double dots is instead of double hat, and here we have Q1 plus infinity vertex Q W algebras, probably due to Niegut, for example. I think Niegut constructed these generators in terms of shuffle algebra. And check.
We need positive part of G1.
No, I don't. I mean, there's no. I don't say this is flat deformation. So if you want to have the size of algebra changes in this. Also, double algebra is also embedded into the positive part of the in the
conformal limit is subtle and still there are some questions, but people did it. Because it's technically not so nice.
Okay. Anyway, so this algebra depends on these parameters Q are just exponents of parameters epsilon, which I had before. Some, I don't know, parameter h. So the condition the sum of epsilon is equal to 1 in terms of Q stands at the product is equal to 1. Now, for this algebra, we have standard Fock representation. So we can take Fock representation of the toroidal algebra and then take a limit and consider it as a representation of Yangian. Or if you know Fock representation of the Yangian, you can start from that. What is important for me now is that this Fock representation depends on one of these Q's. So there are actually 3 Fock representations. F1, F2, and F3. Okay, F depends how to say central charge of F is certain Qi in power 1 over 2, where I is 1 or 2 or 3. So we actually have 3 types Fock models. And also it depends on some continuous parameter which is known by U. U is something like evaluation parameter. The quantum toroidal algebra or Yangian is a quantum group. So one can take tensor product of the Fock models. So take tensor product of the Fock models of the I1, I2, set AK. And this is again will be representation of the of this algebra. It depends on whether you're seeking in conformal limit or in for quantum. I mean, it depends what do you mean by F. I don't know by L any reducible representation, by F any Fock representation, and there are Fock representation of both. Okay, but now let me specify the image of the Yangian. Let me state in conformal case. In the endomorphisms of this tensor product of Fock models commutes with certain screening operators. This K? Integer. And these screening operators can be read from the case where we take tensor product of 2. And there are clearly 2 separate cases when we take tensor product of the same, or take the tensor product of different Fock models. And screening operators, so theoretically speaking, it could be more difficult screenings here, and I mean, we know that there exist. But now I'm talking about the simplest case, where the screening operators are given by integral of the exponent of some Heisenberg or something like this. I'm not going to write explicit formula because I don't even have notation. So in order to write it, I need to first introduce some Heisenbergs here, Heisenberg here, then a certain linear combination of them, which is Heisenberg on the tensor product, and exponent of which will compute with the image of the algebra. Instead of this, I will write the commutation relation. I will write the number of screening. I will write the commutation relations of them. So if we have a tensor product of two Fock models of the one type, we have actually two screening operators. Let me write here 1, 1 as the upper indices. And we have two of them, so one of them will be denoted by plus, another by minus. And they're just, again, the same formula. Integral of exponent of some current, S11 plus of Z. GG. And here's the same formula. If we take tensor product of different Fock modules, then we'll have only one screening, S12. Of course, I cannot say that I will always consider the model, so first and second type. So actually, below I will use sometimes notations like SII plus, SII minus, and Sij for I not equal to j.
Should you write exponent?
Where? I should, where?
In the definition, in this formula for screening.
Exponent here, where else?
No, okay, just look off exponent S plus 1 on Z.
Ah, no, I shouldn't, yes. Yes. Sorry. Yes, so I mean exponent, I think of this S plus as a vertex operator, so this itself some exponent. If I have two vertex operators, say E in power alpha phi of Z, E in power beta phi of W, then and take the normal ordering, then I get something like Z minus double in power maybe alpha beta. So the commit and this normal origin is a origin of any commutation relation between the screening operators.
So what is this equality? What does this equality say? Normally order, then we have this.
Yes, we have this factor. So I want to now I come to the point where I want to write formulas more or less correctly. So let me do this. First, what I want to say is that if I take the S11 plus of Z S11 plus of W, and take this normal ordering, then I will get Z minus W in power minus 2 epsilon 2 of epsilon 3, and then normal ordering. So each of these, okay, let me state it in another manner. So for each screening we have a vector. Each screening S is exponent, if not screening current, is exponent of the scalar product of certain vector S, I don't know, curved, and phi 1, phi n, phi k, where k is numbers above. And the commutational relation between different screenings is governed by the scalar products of the corresponding vectors. So actually what I need to specify is I need to specify the matrix of scalar products of the all screening which acts here on this tensor product. Okay, let me write an example. So if I take the tensor product of k models of the one type, then I have the 2 times k minus 1 screenings. I have screenings S11 plus here and so on, S11 plus here. And for each sign of tensor product, I have pair of screenings in opposite direction. And S11 minus, S1, S11 minus. And okay. And the gram matrix for this, for the plus sequence, is something like this: 2. Okay, is just minus epsilon 1 over epsilon 3 over the following times the following matrix: 2, 2, 2, minus 1, minus 1, minus 1, minus 1, 0, 0. This is a Cartan matrix for SLK. For I am afraid that I'm losing the audience. Maybe I can ask a question. Could anybody guess what will be for S minus? What will be the difference? Yes, so I should write this. Everything is symmetric with respect to epsilon 1, epsilon, the permutation epsilon 1, epsilon 2, epsilon 3. I choose pick 1, epsilon 1 here in this tensor product. So I have symmetry permuting epsilon 2 and epsilon 3. So here I will get just epsilon 2 and epsilon 3 and the same Cartan matrix. And screening and the scalar product of the screening which correspond to different families will be integer. So they are formally commute. We don't have monodromy if we if we include both of them into the correlation function. So what I'm trying to say, so if I have tensor product of two Fock modules, then I know the screenings which we have here. If they're the same, I have two screenings. If they're different, I have only one screening. If I want to write commutation relations, then I need to take tensor product of three. Okay, E1, E2, E3. Then I have some screenings here, and they interact. They have conversation through the common factor, Fi2. And this is why I probably can have some non-trivial commutation relations. If I consider some huge tensor product, then the screening which I consider do not interact because they act on different Fock modules. This is why this matrix has so many zeros. So if I have screenings which act on these tensor products, they interact through one common factor, but other they don't. I don't know. Is it clear, Roma? Is it clear why this matrix has so many zeros? In the means, I will consider tensor product of different Fock models of different type. Yes. Maybe before I should just say that this set of screening, this is the set of screening which define W algebra of GLN hat. And this should somehow be in the agreement with what I said before, that this representation, I constructed said that there's a representation of the affine Yangian, but there is an action W1 plus infinity on them. And W1 plus infinity has a quotient which is ordinal W algebra for GLN. I don't know whether it's written on the blackboard. Here. And this is a construction of this quotient. I take the corresponding representation of the Yangian, and action of W1 plus infinity on it is a how to say the image. There is an ideal of the W1 plus infinity which acts by 0 on any tensor product of n Fock models of the one type, as the quotient by this ideal is the W algebra for the GLN. Okay. Now, what happens if I multiply Fock models of the different type? For example, I can multiply F1 and F2. I get the screening S12, and something maybe, and it happens that this screening is just fermion. So we again obtained something rational. You can think about this as some of the corresponding vertex algebra of some sort of C equal -2 vertex algebra. And the algebra which commutes with one's fermion screening is the logarithmic extension of of symplectic fermions of the C equal -2. Okay, and what happens if we have tensor product of this is how screening itself, this is what happens on the diagonals. So on the diagonals we have either twice ratio of epsilons -2 or either one if we have Fock models of different type. And now what happens, how do they interact? So if I take, say, F1 times F2, then the matrix will be the following: matrix of and S11 minus commutes with S12. In other words, in this case, we have what? We have one screening S11 plus, another screening S12, which acts. This is S11 plus acts on the first tensor product of first two factors. This is S12 acts on the product of the last two factors, and also have screening S11 minus acting in the opposite direction, and this set of screening can be decomposed into two parts, two clusters. I don't know how to say. This and the two groups, okay, and the screening from different groups formally commute. This should resemble what we have in ordinary W algebra, where we have screenings plus and minus, which are formally commutes, and each of them forms some sort of nilpotent, something like nilpotent subalgebra of the quantum group corresponding, but there's a different quantum group with different modular transformed parameters Q. Here we again have these two quantum groups, two groups of screenings, but them are, I don't know, have different size. One of them is still correspond to something like SL2, and in another we have one special screening fermion, and it can be argued that this is somehow correspond to SL2 1/1 to superalgebra. Let me give one more remark. That consider again this tensor product and permute factors. So one can take F1 tensor F2 tensor F1. Since we start from the quantum group, this we have a matrix, and this model is isomorphic. So the double algebra which we get in the image should be isomorphic. But the set of screening is different. So here we have one screening S12 which acts here, another screening S21 which acts here. And the corresponding gram matrix will be something like 1, 1. And here will be some number which I forgot, but probably this is something like epsilon 1 or epsilon 2. Something like this. So we have two fermionic screenings which generic scalar product. I think some part of the audience thought that this week somewhere. So you can ask what is the algebra which commutes with this set of screening. Answer will be this is just a fine SL2. So we have two descriptions of affine SL2. So this description is the following: that you take Wakimoto realization of affine SL2. It has its own Wakimoto screening, but Wakimoto realization is not is realization in terms of beta gamma system. If you bosonize these bosons, then you will get one more fermionic screening which is used to this bosonization. This is this S11, S12, and S11 plus. And this is another description which starts from two fermionic screenings, what with generic scalar product. And the equivalence between these different descriptions is some sort of fermionic reflection, if you want, or just permutation of the factors in the, which is possible due to existence of a matrix. Let me state as a proposition. Algebra which commutes with screenings for F1 times F1 times F2 is affine SL2. Maybe I need to take here piece which commutes with A0, but maybe it's too detailed. As I said, okay. So now I can give definition. The algebra YLMN is a algebra which commutes with screening for I take tensor product of the L models of the first Fock models of the first type, then tensor product of N Fock models of the second type, and then tensor product of N models of the third type. If you think about the size of this algebra, it has L plus M plus N bosons. For example, here we have affine SL2. It has 3 bosons and 3 factors. I don't know, maybe this should, I still don't have much time in order to write everything in the best manner, but maybe there should be a definition of some sort of theorem, which I'm not sure is proven or not. And definition should be that this y is just a quotient of w1 plus infinity by the ideal which acts by 0 in any such tensor product. So there is a standard question in this story. Is it true that the commutational relation with these screenings determine this image? Do we have sufficiently many screenings, or maybe we lost something? For example, if you want to see, is it possible that we lost something? You can look at this example. So you see here, before permutation, we had 3 screenings. 2 of them form something like affine SL2-1, and 1 will correspond to dual SL2. Here we stay only with 2 screenings. Then it is natural to believe that they correspond to affine, again to SL2-1, just another Borel subalgebra with only fermionic simple roots. But where is the analog of this screening? So something is absent here. It exists, but it is not exponent. But anyway, it exists. Okay. What do we know else about this algebra? We know quite a lot. For example, we know formula for central charge. It is, if we denote by lambda I then central charge C is something like lambda 1 minus 1, lambda 2 minus 1, lambda 3 minus 1. Maybe plus 1, or maybe not. Maybe not. When I say that this algebra which acts somewhere, this is maybe, I mean, if I'm talking about vertex algebra, I need to say something about its vacuum model. I said something that we have vacuum model for W1 plus infinity, take the quotient. But for example, what is the size of this quotient? Okay, but then we should be more logical and first ask what is the size of the vacuum model of W1 plus infinity. So we take here trace of L0 of say Q in power L0 of a vacuum model. This is easy. This is if we know PBW theorem, which is probably people from the first who see near can even still read here, despite of my attempts. Then it will be product by d from 1 to infinity. Oh, let's write by n from 1 to infinity. Okay, d product from n from d to infinity 1 minus q in power d. We have PBW theorem, so the size is of the model is a size of polynomial algebra, and this is a degrees of generators. For W1, first we have generators of each degree, 1, 2, 3, and so on. For W2, generator degree starts from 2, and so on. This formula can be rewritten in the form that this is a product for all n. Q in power n. Okay. Artyom, okay. And this is sum of 50 Young diagrams U in power number of boxes. And this is McMahon. So this and we have the similar answer for the YLNM. So for we do not have such simple formula. So so in principle, we do not, instead of, if L and M equal to 0 and N is alive, then this is standard W algebra, and we have the product just, the first product just become finite and everything is okay. We have good formula. If all this, at least two, even if at least two of these numbers are not 0, then formula becomes more cumbersome. It does not look like a one of a product. This is not the character of the polynomial algebra. This is somehow should be reflected to the fact that center of the superalgebra is not a polynomial algebra. Is not even if you take say GL11, it's not it has infinite number of generators. But so in principle we have some formulas in between which I'm not going to write here, but let me write the answer. We have Q in power number of boxes, and the summation goes over 3D Young diagrams with a pit condition. Without box with coordinate L plus 1, M plus 1, N plus 1. So we have for our, I cannot draw it, I apologize. So I can draw only for plane, if you prefer language of plane partition, so you have a sequence of numbers, say n11, n12, and so on, n21, it's small, a11, a12, a21, and so on. With the plane partitions with the conditions aij is greater or equals than aij plus 1 and greater than or equals than aa plus 1j. Then this speed condition means that a n plus 1 m plus 1 is less than L plus 1. So this plane partition is just projection of the three-dimensional Young diagrams. On each box I write the height of the corresponding column. And this is condition of the height of here, of course, which has this condition has many consequences of the heights above and below. Okay. Now, what we can say about representations? Something has been already mentioned, that this algebra has Fock representations. It is, in my approach, it was defined through its Fock representations. It is less trivial, but combinatorially more nice and more motivated. That this algebra should have representations which should have the following description, combinatorial description. So there are the representations which depend on the, say, three Young diagrams, lambda, mu, nu, such that the trace, the character is again q in power number of boxes, and summation goes over 3D Young diagrams without box and with asymptotic behavior, asymptotics lambda, mu, and nu. We have three directions along the coordinate axis, and we have here I just suppose that we have standard Young diagrams with finite number of boxes. Here there's generalization similar to which we have in topological vertex, but now we have some sort of topological vertex with additional conditions without a box.
What's the logic? So you like consider representation with some fixed L, M, and N. Then you consider an algebra which is the image of W1 plus infinity and then you are saying that this algebra by element has a different representation vacuum, which is much larger than.
No, this is smaller. Let me explain. First, assume that L and M are equal to 0. Then this speed condition can be viewed as the restriction of the height of my three-dimensional Young diagram. It has height not greater than m. It means that we have a sequence of n Young diagrams. First part and second. We have no more than n diagrams with additional conditions. If we put one on another, with construct from some three-dimensional Young diagram. With boxes do not fail. We have it will be just three-dimensional. So we have less the tensor product and Fock models. If you have now make all the L and M and are alive, you still can cut your three-dimensional Young diagram into N plus M plus L ordinal two-dimensional diagrams. This, and this. With some quite non-trivial condition. So this size of the representation is less. Actually, you can.
But okay, you have like bench of Young diagrams which are like section of your 3D Young diagram. But no, but like what infinitely many. Infinitely many sections.
No, due to P they have finitely many. Oh, are you asking about a case where L and M are 0 or generic?
Generic.
In generic, I can do section in different directions. I take L section horizontal, then M section vertical.
Okay. And you are claiming that the L section in one direction, M section in another, and N section in the third direction uniquely defines
Yes, because 3D Young diagram lives in the union of the corresponding sections. This is due to Pitt condition.
no, actually
Okay, I need to finish soon.
So this character which you wrote, is it the character? No, it's not the character
Of the Fock?
of the form.
Not.
It's a character of some representation.
This is no, this is not Fock. This should be viewed as an analog of this special representation, like for Virasora, which we have like MN representations. So it is probably still conjecture, but there exists a resolution of some sort of complex which consists of Fock models whose cohomology is this. Okay, now what I should finish, and I want to finish with gluing. There's a paper by, again, Rabchak and Prohaska. I'm not sure about names, about spelling, where they did the following. They consider three-valent diagram. This is not necessary to be. It's not necessary to be a tree. And for each vertex, they assign this Y algebra. They put numbers, and 1, and 2, and 3, and 4 to each face. So for each vertex has this form, L and M. And for each vertex, they assign corresponding Y algebra. The ordinary Y algebra corresponds to this this sort of vertex, and if any other vertex is obtained from this by action of SL to Z, which acts, for example, on our parameters epsilon 1 and epsilon 2. So epsilon parameters, which correspond to central charge, for these two vertices for this algebras will be different but related by some SL2Z transformation. And more or less, vacuum module, which correspond to this picture, will be summation of the model of the tensor product of the models of these Y algebras, where summation goes over the internal edges of the diagram, which lives on internal edges. And this is a bit another class of vertex algebras, which of course contains many known examples. In particular, if you take, if you think that this is too difficult to start and take just two vertices, then you have SL2Z three cases. They can be put it like this. They can be put it like this, or like this. I will fix the left vertex and do T transformation on the right side. And assume that we put numbers in this way. Then each vertex will correspond to W algebra of GL2, so Virasoro plus Heisenberg. So this is again coupling of two Virasoro algebras. And the value of parameters, the resonance condition will be, okay, so today, in the morning I calculated and thought it will be values like 0, -1, and -2. So -1 and -2 are the examples which I mentioned, and 0 is one more example. Maybe I made a mistake in this calculation, but anyway, it's time to stop. It's already half an hour.
Also two epsilons here in their construction.
For each, I mean, here we have epsilon 1 and epsilon 2, and epsilon parameters for any other vertex are obtained by action of SL2Z.
So only two free parameters.
Only two free parameters. Epsilon 1, epsilon 2. I mean, I don't know. I mean, it depends what do you want. If you want something like W plus infinity, and probably you won't, then you need to take analytic continuation with respect to this M parameters which lives in faces. And then I think you'll have more parameters. But I don't know, does more means one more, or maybe means, I think just one more, but I don't know.
Questions?
Sake of operation.